like the panelists to communicate with me through raising their hands on Zoom, so I know you have something to say. And I'm going to ask the rest of us to communicate through Slack. So, so I'm going to ask then the panelists if you've seen a topic, and this includes Kate, if you've seen a topic raised in the Slack that you'd like to talk about, please raise your hand and I'll have you talk about it. Are we all there, panelists? Well, then I'll ask the audience. What questions do you have? Let's see. Yang.
Yes. First of all, Kate, this is a really, I have my camera in a weird way. Never mind. I'm going to close my camera. So this is a really great talk. I really enjoyed it. I have a questions about your 2012 work, where you say that you find 6 galaxies with inflows and most of them with high inclination angles. I think that's really interesting because I always have this image in mind that when you see a galaxy that is mostly edge-on, then you see through everything with this halo interface. Basically, you find a star in a disk in the edge-on direction, or mostly edge-on. In that case, your line of sight has to go through a very thick layer of the disk halo interface, right? So I was wondering, does that disk halo interface give you any signals that could result in redshifted or could be confused with inflow? Does that make sense?
I guess I'm not totally clear on the geometry you're thinking of. Oh, you mean if it's mostly edge-on but not exactly edge-on, then you have a really long view through the disk.
Yeah.
Right. And so maybe if you have like a lagging extraplanar layer or something like that, that could induce a significant redshift.
Right. I'm not sure if that would result in either blue shifted or red shifted. So I was wondering if you have tried to do this modeling and see if that signals would give you one direction or the other direction. Yeah.
So I think if I recall correctly, and others, if others have thought about this, I did think about extraplanar layers a bit inspired by your paper. And I believe what would happen is there would be half of the galaxy. If you have a lagging extraplanar layer, you would detect red shifts towards half of the galaxy and then blue shifts towards the other half. And the magnitude of the red shifts might end up being larger than that of the blue shifts. And this is more extreme the more edge-on the galaxy is. So you could induce, a redshifted absorption line signal, but I think it would only be over half of the galaxy. And so since in that work, our spectroscopy was integrated. So it was just, it's dominated by the light towards the center of the galaxies. And we're detecting, and we're only going to detect inflow in those systems if it covers most of the disk. And I think that like the lagging layer model, can't quite do it.
Yes, that makes sense to me when you mentioned it's an integrated light. So yes, yeah. I think I was missing that. I thought it is like very small pencil beam through one particular chunk of the disk, in which case you could get either signals. Yeah.
Yeah, so these galaxies are really far away, they're only an arc second across or so we can only collect all of their light at once.
Cool. Thank you.
So panelist Claude-Andre has a hand up.
Hi, so this is actually a question for our speaker, Kate, if that's okay. So great
It
talk.
is. It's fine.
In the first part, you mentioned evidence for accreting gas in the form of what I might call low metallicity spots onto galaxies. And in the last part of your talk, you mentioned evidence for inflows from redshifted spots. So the question is, do these correspond spatially?
Oh, that's a great question. I have no idea, but that would be really interesting to look at.
Can you remind me of what the data in both studies from manga, such that in principle it would be straightforward to check?
Totally, yes. Same galaxies.
Yeah, so that'd be
Great idea.
check. It occurred to me that the frequencies you quoted seem similar, 10%-ish. Okay. Thank you.
So one of the questions that jumped out on the Slack for me was Dylan Nelson's asking, what is the future for complex absorption profile modeling when we should always assume a mix of 1 inflow, 2 outflow, 3 rotating disk, and 4 emission infilling? Does anybody dare to tackle that one?
I welcome others' input.
Calling out to other panelists.
I don't think I would dare to start to tackle this one, unfortunately. I mean, it's just, yeah, I mean, it's just too complex, I think, for now.
Right. I guess the general question is the nature of what we can do observationally is quite a bit different from what people are capable of modeling. So I think we're all trying to figure out how do we make better contact between what it's possible to observe and what it is possible to model. So I'll ask Claude-Andre, if you could ask the observers to do something, what would be your dream thing for them to be able to observe?
Let me make sure I understand your question. So the dream thing that I would like the observers to observe.
Right. So we want to understand how inflow happens. If we have seen the talk told us a lot about what it's possible to observe right now, and I guess I'm wondering, if you had, knowing what you see in simulations and influence simulations, what would be the ideal observation to be able to make?
Right. So I just wanted to clarify, is this connected to Dylan's question about the large number of components in the observation, or is this an independent question?
It's an optimistic way of phrasing Dylan's question.
Yes. What is the ideal thing? Well, I'm not sure what the ideal thing is, but one thing we haven't heard too much about is how to detect inflows in the hot gas, which I think can be quite important. I think it could even be dominant in not only in massive elliptical galaxies, but also around some L-star disk galaxies. In fact, in our fire simulations, we have a recent paper led by Jonathan Stern in which we correlate the emergence of hot halos, in particular hot gas in the inner CGM, with the formation of large galactic disks. What we haven't quantified is when these galactic disks emerge, what is the fraction of the total accreted gas mass that is cold versus hot? So I'm not sure what the answer is, but I think it is plausibly dominated by hot gas accretion. And I think it would be great if we could have better observational constraints on cooling flows of hot gas onto galaxies.
And just from one, I totally agree with you on that. Sanch.
Hi, first of all, Kate, that was a great talk. And in that same spirit, from what Kate showed and what Dylan is asking, I think we know very little what we are looking for. So there have been different aspects to it, as Kate mentioned. There is a metallicity component. Clearly, very low metallicity is inflow probably. Certainly, velocity is probably the best indicator of something coming in, but you could have higher metallicity gas. So at least as far as I see, we have to sort of, especially for absorption line, and that too using a background quasar, I think in my opinion, although it's very hard, I think will be the easiest thing is to sort of break down different aspects of it, like using maybe along the disk where you feel like the rotational component is going to be the maximum, or then have a sample which is vertically. So just to break down Dylan's question, I think the one thing that it has been very hard to do, and hopefully in the future we can have very large samples, the idea would be to just break down samples into these components which would have minimal contribution from one aspect or the other. And to do so, I think what would really help is for observers to know what is expected. And I know that there are a whole lot of things going on, and certainly it's not easy to disentangle in a simulation. But if we can identify a sample of galaxies, maybe a quiescent galaxy or a gas-rich H1 galaxy without a whole lot of star formation, if you expect a lot of inflow along the disk or from on top, some of those predictions might really help us identify samples that can probe one aspect of it. And then finally, everything put together can probably tell us rotation, inflow, outflow, and everything else. But yeah, so we don't really have a sample to do so. And right now we're struggling to fit everything to one sideline through one galaxy, which probably is very hard, but that's the best we can do.
I was about to say something. Filippo has a hand up.
Hello. Thank you, Kate, very much for the very nice talk. I like the story also very much. At the beginning, I didn't know what you were going to tell us at the end, and then fortunately at the end you said everybody is right. So I want to add to this and say that given that I'm on the side of the vertical inflow, I said it so strongly, but I actually I perfectly agree that there is going to be inflow also along the disk and in the outer parts, because we see lots of gas in the outer disks of galaxies, and that gas has come from inflow. So what I was trying to say, and what I think should concern us, is where does the gas that is going to form stars in the galaxies come from? So that is the main question. And if you have gas coming vertically onto the disk, the gas is already there, and that would certainly form stars unless it gets ejected again. If the gas comes in the very outer part, then it has to get to the center before forming stars. And that's a process that I'm not sure, as I was saying, we see occurring, at least with the efficiency that is needed. But going back to the question that was asked before in the discussion, I had two things to say. So when we look in the mission, like Kate was showing, the extraplanar gas, there we can really model everything, because we can model, we can have kinematic models or dynamic models in which there are all the components, all the velocities together, and we do see these general flows that I think is very general, that galaxies show a general flow going into the disk. But also with absorption, and this is something that I started to do a little bit in the last period. I think there is lots of potential with this very large surface to put together galaxies and work statistically at and to some extent, it's extremely difficult, and we all know, to understand what's going on from a line of sight. But there are thousands now of line of sight. So let's try to work up models statistically that can statistically interpret these observations, because I think there is lots of information. I mean, many people have done it already, but I think that's the way to approach the absorption studies.
Okay.
So sorry, I
Chang-Goo.
don't have a question. I was just
yeah. Okay. Chang-Goo Kim has a hand up.
Yes. Since you asked about the some theoretical or the theorist expectation from the observation about the inflow, and kind of the things that I learned from my simulations, although because it's a local simulation, it always have some limitation. But what I learned is basically when we have this inflow dominated phase, that's always come with some kind of the deficit of the star formation, basically. So since we basically when we turned off the feedback, then you can actually kind of dominate by the inflow. So I'm not sure. And then the large scale inflow, and this is about the fountain flow driven inflow, so that if we kind of probe the gas inflow near the disk, and we can basically measure both inflow and the star formation rate with a kind of the like a short-term instantaneous star formation rate tracer, not instantaneous, but it's with some short time scale like H alpha type tracer. And if you have some spatially resolved observation and correlate that, whether if those are when you have inflow, if those are kind of the come with the low star formation rate spectra, then I think it's mostly we can say it's more about the fountain driven inflow, I think. And because this when star formation has shut off, then there are no kind of the hot gas is not really created by the supernova feedback. That means now the kind of this 10 to the 4 Kelvin type temperature gas are filling the volume and falling back. So that's what is seen in my simulation usually. I'm not sure whether this really valid even in the global simulation, but I think it's generally have I think I may expect more larger covering fraction of the inflow when it is dominated. So.
Thank you. And I see Greg has a hand up, and there's something I wanted to, if you can hold on to that hand. There's a theme that I believe, yeah, thank you, Greg. There's a theme that I kind of has seen emerging in what people have been asking on Slack. And if I can bundle it into an idea, it's we measure inflows and outflows, and sometimes we tend to talk about what's going on in terms of inflows and outflows. But from a galaxy evolution perspective, it's important to be distinguished between circulation and fresh inflow, right? So there has to be some net inflow for a galaxy to continue to thrive. And a significant amount of what the galaxy does is circulating, which creates both inflow and outflow, but doesn't lead to mass, long-term mass ejection. And so the question then is, how do we distinguish these things? And among the suggestions, and there are people in the panel who have thought about this, there's using metallicity as an indicator of what is circulating and what is fresh. And I think there's emerging appreciation that angular momentum is also an indicator of what can be fresh and what is circulating. So what are your thoughts about how we distinguish between circulation and fresh supply?
Well, if it's fresh supply, you do expect that the metallicity is quite low, no?
Okay, well, yes.
So,
and how,
and we do,
oh, go ahead, please continue.
Sorry, and we do find, you know, when we study Lyman limit system, which are the dense region in the universe, that basically when we find a Lyman limit system, we find a galaxy near it. What we find is that you have lots of this very low metallicity gas. And when I'm saying low, it's 1% solar metallicity or less at low redshift. And that's basically the same metallicity that you have, that you found at high redshift. That's basically in this same system. So that means that you have a lot of this gas that is around galaxy, very low metallicity that has not been polluted by recent star formation. And so we, you know, what this gas is doing, yes, we don't know if it's actually inflowing, but I think we can argue that it's not outflowing because the metallicity is so low. So you know, there's been a lot of questions earlier in the conference about, you know, what's the use of metallicity? And I think there is still a use for the metallicity, because when we, you know, when we talk about 10% solar metallicity in a higher, lots of things can happen, and that's what we find in our Milky Way halo. The Milky Way halo, the HVCs are in typically about 10% solar metallicity, or higher. The margin stream is about that metallicity. And Filippo has shown that you know, this type of metallicity, you can just get them by recycling the gas. Galactic Fontaine model, and you have other model. For a long time, HVAC like complex C, people were arguing that was like pristine accretion on the Milky Way halo. I will argue that's clearly 10% solar metallicity is not pristine. But when you go down to 1% solar metallicity or lower than that, and I still ask the question, you know, what this guy is doing around galaxies. I know we do a similar study at higher redshift, and we find, you know, 0.1 solar metallicity, or even lower than that, in these pretty high electron density observers. And in my opinion, that's, you know, when you look at least at some of the diagnostics that the simulation have been arguing for these inflows, is that it must be ionized, it must be pretty high electron density, and it has to be pretty low metallicity gas. So yes, we can't show with the observation yet that this gas is actually inflowing onto a galaxy, but it's around galaxies. So what it's doing from the observation alone, I do not know, but there is quite a large fraction of it. So how do we go to the next step? I'm not sure, but I think we will rely on more and more comparison and with simulation. And
I'm going to prioritize, we have a lot of hands up, and I'm going to prioritize panelist hands. Claude-Andre.
Yes, I just wanted to add a theoretical perspective to what Nicolas said. And I think what I'm going to say is largely consistent with what he stated. So Zach Afen has done particle tracking analysis of the fire simulation. So in the particle tracking analysis, you know rather unambiguously whether the gas is falling in for the first time or whether it's been another galaxy before and is recycling. And what is shown in the simulation is that very low metallicity, so over the 1% solar, can tell you with pretty high confidence that the gas is falling in for the first time. But there is a pretty broad range of ambiguous metallicities, intermediate metallicities of order 10%. for example, where the gas can either be falling into the galaxy for the first time or recycling, and the way that it can have this kind of intermediate metallicity but still be falling in to the central galaxy for the first time is because the volume filling halo can have been previously enriched with metals, and then the gas is falling in from the large gas structure for the first time, but it sweeps up and mixes with some metals on the way to the central. So very low metallicity in the simulation is a very good predictor that the gas is accreting for the first time, but a lot of the gas is at intermediate metallicities where the metallicity alone does not unambiguously tell you whether it's falling in.
Okay. So Sanch has a hand up, but I just want to plant a seed. No one has to answer this, but have people looked at all for metallicity angular momentum correlations and whether they could be exploited? So I'll put that out there and then ask Sanch what her question is.
I just have a comment. I want to be very quick because there are people waiting. Related to the circulation versus fresh inflow idea, clearly the two things that you mentioned, metallicity and angular momentum, are very, very good tracers. But statistically, one of the results from COS gas is that the halos of H1 rich galaxies are rich in gas, and it's more strongly correlated to H1 mass than star formation. So we think that this could be fresh gas because circulation would probably be enhanced with star formation rate. Another result, which is not out, but it's in submission, is that the H1 rich galaxies are strongly correlated to Lyman alpha absorbers. So these are absorbers where metallicity cannot be measured, column density of 13 and 14 per centimeter cube, so in log scale. So essentially, then emission line star forming galaxies. So in some sense, with these broad observation, although we cannot say this particular absorber is an inflow versus that, but overall, the sense that the H1 rich galaxies are surrounded by these bubbles of gaseous, in the intergalactic medium up to 1-2 megaparsec away, which is clearly outside their virial radius. So essentially, I feel like with all these independent measurements, we do have a sense that there is a bit of fresh accretion going on, although we don't know exactly which absorber is tracing fresh accretion.
Okay. Now, I've made Greg wait long enough, but Ramel and Young had raised their hands during this discussion, so we'll have Greg ask, and then we'll return to those other hands. So please, Greg.
Well, actually, maybe instead of asking my original question, I'll just say a few things. So I just wanted to agree with what Claude-Andre said, which is that it's actually quite challenging to distinguish between, inflowing and outflowing gas, particularly on metallicity alone. I actually was thinking very much along the lines of trying to look at correlations in angular momentum and metallicity, as you suggested, Mark. And in particular, cosmological simulations, tend to show that the inflow is occurring preferentially along the disk plane with this, and with high angular momentum. And then the final thing I wanted to point out is that of course, is an obvious point, which is that material, which is undergoing some sort of recirculation, is typically not found very far from the disk. So inflowing gas at large radii, which of course is observationally challenging, but it is a good sign that that's not being recirculated. And actually, let me just squeeze in my original question, which is, so the observers have, so first of all, Kate, beautiful talk. There's been a lot of work, Mary Putman, a few others, many others have looked at the inflow rates in the Milky Way in particular, but other galaxies as well. But in terms of mass, but I'm interested if there's, what's the prospects for doing it on a larger scale for the angular momentum inflow rate? because of course, disks we think are still being built up from the inside out. And so the expectation is that the inflowing gas, especially if it's pristine, has more angular momentum. I'll stop.
So you're asking for Kate to comment, correct? Oh. Greg went away.
Well, gosh. I mean, in the Milky Way, people should correct me on this, but in the Milky Way, I think, people are, Filippo, for instance, has demonstrated that the HVCs can be explained by a fountain model. And so I don't know that we have examples in the Milky Way of complexes that we know to be fresh inflow, unless we would consider the Magellanic stream to be fresh inflow. And so then, I mean, we must have great measurements of that angular momentum. But if we already know it's fresh inflow, I'm not sure what we're learning from that. When it comes to other galaxies, I don't know. I mean, I think Crystal Martin's work, maybe she can comment on, she's put constraints on the angular motions or azimuthal motions of gas or in the halos of galaxies. Perhaps there are prospects for also measuring that gas's metallicity, maybe. I don't know.
Yeah, I could just say real quick, the hard part is getting the hydrogen column.
Yeah.
Right. Indeed. All right, Ramel's had his hand up for quite a while, so we'll have him next.
Cool, yeah, so yeah, going back to sort of the metals and angular momentum question. So we looked at both of these things actually in Charlotte Christensen's Zooms a few years ago, which are similar to the Nihao simulations in their input physics. So I think in terms of the metals, I think what Claude-Andre said and what others have said is largely reproduced in those. In terms of the angular momentum, maybe I'll just mention a result that might be a little bit surprising to people. So when we tracked the particles, we found that the particles that were ejected were reaccreted with an angular momentum that's typically significantly higher than what they left with. So a factor of typically 2.5 to 3 times higher. So that's when they rejoin the galaxy. So in point of fact, it's not totally in fact, I would say it's just the opposite, that the reaccreting material is actually higher angular momentum than just sort of regular inflow material, if you think the inflowing material basically is responsible for the angular momentum of the disk. So so that's sort of we didn't do a direct comparison to the inflowing angular momentum, so maybe we should have done that, but I'm just saying that like what happens in the disk is that, or what happens in these outflows is that they go out and they basically get torqued up as by the halo gas. They get sort of swept in and they pick up a lot of angular momentum out there. So so it's a little bit more complicated. So I don't know. I think it's a really interesting idea to look at this correlation between angular momentum and metallicity and see if there are regions of parameter space that would be identifiable for that. But yeah, the angular momentum story of galaxies is actually pretty complicated, and of course, it's part of the reason why we can now produce things like bulgeless disk galaxies, where in the original ways we couldn't, right? This is exactly the process that does it. So anyway, I just wanted to mention that.
Okay, thanks. Young has had her hand up for quite a while.
Thank you. So I have 2 questions. The first question I asked in the Slack already, which is how do we actually measure the angular momentum in observation? Because if you look at the Milky Way observers or in H1, we only get a line of sight velocity. We don't get a transverse velocity, in which case you don't really have angular momentum estimate, right? So does it involve any model assumptions? So that's my first question. The second question is, going back to your earlier question in terms of how to distinguish between inflow and outflow, whether we can use metallicity, angular momentum. The third parameter I'm thinking is perhaps the line width or Doppler width. So this is a question for the theorists, especially for those people working on turbulent mixing interface or understanding how cold gas mixing with hot gas. So do you see a change of Doppler width or line broadening when you study the evolution of cold clouds mixing with hot gas and eventually coming back to the disk? Is there a change from smaller B value to larger B value, or the mixture of everything? And does that tell us any signatures of inflow and outflow? So that's my two questions. Thank you.
So it's directed to the theorists on the panel.
I think the first question, Crystal wanted to comment on the angular momentum.
Sure. Real quickly, in terms of measuring angular momentum, it's a derived quantity, right? In the sight line, we measure line of sight velocity and impact parameter. We've argued that if you know the orientation of the galaxy, the position angle of the quasar, the inclination of the disk, and which side of the disk is closer to you, then you can make an assumption. You can say, if the absorption along the line of sight is in the plane of that thin disk, then this would be the radius in the disk plane, and this would be the velocity in the disk plane. Then you have a specific angular momentum. You can do the same thing with a thick disk model and a vertical velocity gradient, although there's a few more parameters involved then. So it's very much a derived quantity.
Okay. Do any theorists in the panel want to respond to the second part of Young's question? You can always raise your hand and respond at a later time.
Or this could be a pet project for some theorists to take a quick look at their data. I'll be really interested to know what's going on.
Yes, pet project for sale. There you go.
Yeah.
Okay, Filippo had a hand up.
Yes, thanks. So this was a reaction to Greg's question and also what Young just said. So I agree that in the Milky Way it's almost impossible to measure the angular momentum without a model. You need a model of the whole extraplanar material to understand what the angular momentum of the accreting gas can be. So in the phantom model, where there is the phantom triggers the condensation, the pristine gas accretes at a radius that is not so small. It's actually quite large. It's around the peak of the accretion rate is around 8 kiloparsec from the center. And because angular momentum is RV, actually the disk through this accretion is gaining angular momentum. So the disk is increasing through this type of accretion. I don't know if anybody has made a model of the Milky Way, layer, extraplanar layer from other types of accretion. So, but in the phantom context, the inside out is preserved, and the angular momentum of the accreting material is larger than the average angular momentum of the disk, which is important.
I'll get to Nir in a second. I want to, Ben Oppenheimer in Slack is saying a lot of simulations, Eagle especially, show a lot of angular momentum in the hot phase. In fact, there may be more angular momentum in the hot phase than the cool phase. And in that context, if people aren't aware, the angular momentum in the hot phase around the Milky Way has been detected through absorption line studies by Joel Bregman and his group by looking at absorption lines in different directions and trying to model velocity shifts. They're able to detect that the Milky Way's hot halo is rotating. The constraints, are quite model dependent, but there is rotation of the hot phase. Nir.
Hi, thanks very much. So I put this question in the Slack as well, and I guess there was a bit of discussion around it, but something that I'm a little confused about is the So when we speak about accretion of cool gas from the intergalactic medium, fresh accretion, which has high angular momentum and is accreting along the major axis, the famous cartoon from the Tomlinson Peoples and work model that always comes to mind is of those accretion streams. However, at least from the theory perspective, we don't really expect these so-called cold stream accretion model to be present except for the most massive galaxies at any given time. At redshift 1, only galaxies above 10 to the 13 solar masses or so. Is the high angular momentum gas, or the largely rotating gas that we're observing, is that a different mode from the so-called thin accretion streams? Is that just condensation and cooling of high angular momentum accreting gas, which might be accreting more isotropically on large scales? Does it connect intergalactic filaments? Is it the same phenomenon or a different phenomenon?
Okay. So, Claude-Andre, you have insights here?
I guess I'm not sure this is an insight, but I would echo what Nia was saying, which is that the Tomlinson cartoon does not match a Milky Way-like 00 galaxy in the simulations. It's in our simulations, the disk-like Milky Way-like galaxies at 00, they're primarily surrounded by hot gas with perhaps clumps of cool gas falling in once in a while, but they don't have these long-lived thin streams spiraling in. So that picture would be, as Nia said, in the simulations, more representative of a massive galaxy at perhaps redshift of 2. So perhaps this is something useful for people to keep in mind when they are inspired by the cartoon.
Then what are we seeing?
Maybe Jess or other people on the review article can tell us what kind of galaxy this cartoon was supposed to.
I mean, the cartoon was always meant as a cartoon, and in fact, we've said amongst ourselves that it's almost definitely wrong, and we're looking forward to people discussing all the ways in which it's wrong. So this is perfect.
Okay. Yeah. Nicholas.
Yeah, on this topic, I don't think observationally we know what's going on beyond 80 kiloparsec, and whereas the streams are on the scales of 100 to maybe 2 megaparsecs. So that's one thing. And the other thing is, I thought from the simulation of Avishai Decker that the transition was more redshift 1, 10 to the 12. You could have those streams, and the transition is kind of blurry, depends on the methodicity of the IGM. But it's not inconceivable that there are situations where this picture is applicable at redshift 1. Redshift 0 is a different story, maybe.
While people have mentioned higher redshift stuff, Tim Heckman had a kind of interesting comment in the Slack. If you compare the outward force of the wind to the inward force of gravity, then you can define a critical column density above which gravity wins. On the radial scale of a Lyman break galaxy, this critical column is about 10 to the 22. And the point is that there could be stuff that's falling in like bricks that is relatively invisible because it's so optically thick. Does that cause concern, or is this something we have hope of measuring? Is this a realistic picture for what's going on in high redshift?
So Mark, just to comment, I've had some exchanges with X as well, in the Slack channel, but I just want to emphasize this is talking about gas on galaxy scales, not the CGM.
Okay.
So, I mean, it's mainly just that, gravity falls like 1 over R and on isothermal potential, whereas the Ram pressure is dropping like 1 over R squared. So if you get far out, gravity has an easier time. But this is really just an attempt to explain why we have, hundreds and hundreds of Lyman break galaxy spectra, and you almost always see outflows. There could be invisible stuff falling in that's just optically thick to dust.
Right. I was thinking of this in the context of the difficulty of locating cold streams. But Sanch has a hand up.
Yeah, I just wanted to mention one observation. I want to tag Jess and Rangwon if they're here, and Kate. In general, what we find in CGM is that absorbers are very close to the systemic. We don't see like a whole bunch of floating stuff. In velocities allowed by the Birrell theorem also, and especially the ones that we have H1 masses and profiles. So we can pretty much see the entire rotating disk in velocity. Almost 90% of the CGM absorbers have velocities within the rotating disk, what is allowed within the rotating disk. So I think that's something people can think about in theory when they're modeling angular. Of course, I don't have angular velocities, but the fact that even if it's orientation, we have a bunch of galaxies, the fact that we do not find absorbers with velocities higher than the rotational velocity of the galaxy in the nearby universe is kind of interesting. And I'm sure Jess might add something in, and for cos halos, or Rahman might add something for cos dwarfs. I'm not sure if he's around.
I think that's a great point, Sanch. And I've always been really fascinated by the kind of subvirial, velocities of the absorbers that you see in the circumgalactic medium out to, 150 kiloparsecs. I think that there's something very interesting there, that it's not 100% clear to me that we know the answer. I do like the picture that Matt McQuinn and I presented in 2018. That paper, if anybody wants to go look at it, of this cooling inflow. But I'm sure there are others that can.
Right. So in the Slack,
sort of
go ahead.
Oh, sorry. I was just going to say, I always interpreted this as probably some sort of drag, that things don't reach a terminal velocity. They're condensing out of something and they don't last long enough to actually be accelerated up to free fall, basically.
Yeah, and actually that's part of the picture I think that Matt and I talk about, is that kind of continual regeneration of cool material.
Yeah. And I will suggest it can also be analyzed in terms of gravity waves, but I won't go any further on that here. I'll point out Crystal Martin suggests in the Slack channel we need a Halo 21 schematics channel where we can collect cartoons for inflow phases. In fact, it would be very illuminating to have every meeting participant submit a cartoon so we could see what's actually in people's heads. It would be amazing.
Just visualization, perhaps?
I'm talking about something different. At Aspen meetings, one of my favorite things at Aspen Blackboard meetings is to watch theorists draw graphs of data, because it's not the data, it's what they think the data is. And it's very illuminating to see what people think the data is when they draw it on a blackboard. It may be also very illuminating to see what people have in their heads. If they asked to take a white sheet of paper and draw a cartoon of the CGM, like what it actually looks like. I'm not sure that qualifies as a visualization, but it could be psychologically very interesting to see what's actually in that person's head. No wonder I don't understand what they're talking about, because that's what's in their head when they think of the CGM. That cartoon. Maybe the organizers can think about this, but a gallery of cartoon CGMs might be therapeutic at very least. We have only a couple minutes left, and there are no hands up immediately, and so maybe this is a good place to point ahead toward the rest of the week. Interestingly, a number of the things that have come up in this discussion, there are going to be tutorials on them tomorrow. Nir Mandekar will be telling us about the physics of cold streams. Jonathan Stern will be telling us about the physics of hot halos and cooling flows within them. And I'm sure, having read Jonathan's recent papers, we're going to find out what happens when these cooling flows have some angular momentum, and how is that related to the disk and the formation of cool gas. We think, well, there could be a third tutorial. We're still trying to figure this out, but there will be at least 2 tutorials tomorrow. And then once you're all up to speed on that physics, we'll have Dusan Karish give a more simulation-oriented talk on how does gas get into galaxies. So if you just need more science today, remember that there is an after party at 1 p.m. Pacific on quenching. I've asked them, since I personally can't attend, I asked them to tape it and put the video up. So if you can't make it, there will be a video, I am promised. Do any of the organizers have something else to say at this time? If not, I want to thank our speaker and our panelists for a really, really interesting discussion. I got a lot out of it, and I appreciate everybody's eagerness to participate and share their views and to be clear and pointed about it. So thank you, and we'll see you again tomorrow, if not at the after party. Bye-bye.